we will get started here. First, let's just take a little litmus test in the chat on how you're feeling about the statistics stuff, because I know that it's possibly overwhelming for some of us, right, if we've never done statistics particularly. So let me get a 1 in the chat if you feel pretty good so far about the statistics, what we've done, and a 2 if you're like, this is so hard, I hate it, I have no idea what's going on. Okay, a 1.5, yeah, that's fair. Okay, so we've got like a 50-50 thing here. Now, the good thing is nothing is going to get harder than what you already looked at if you did the statistics lesson 1.2. It's hard, guys. I'm giving you college level statistics stuff here, right? Which is hard. Obviously, I'm not holding you to a college level standard on this work, right? But I want you to understand this connection between math and science, right? And that there actually is useful math. Because I know a lot of math that you do in school, you feel like, what is this? Why are we doing this? No one does this, right? Well, this is the kind of math that people actually do. And I also want you to see that most of this math, we don't calculate by hand, right? Something, a computer, a program, something else calculates it for us, and then we interpret and analyze the results. That's what science is about, right? So looking at the numbers we're getting and what do they mean? The only test that we will calculate is the chi-squared test, which we're going to do today. The R calculation, we will go over again if you guys want. Probably not today, but possibly next week. And of course, that one is computer derived, but you do have to understand how to analyze, right? The Pearson test, exactly, for correlation, right? I picked that one because that one actually is a linear relationship, which a lot of you guys are going to be learning about linear things in math, or you already have learned about them. So it makes sense, right? Y equals mx plus b, things like this that people should remember. And if not, I'm going to help you get them in science here. So what we're going to do is we are going to open our chi-squared lab. I'm going to send you a link in the chat if you don't have it open already. And you're going to want to make a copy of this right now for yourself. You're going to want to make a copy and call it, chi-squared M&M lab with your name, because this is what you're going to turn in. So everybody right now, go ahead and take that link, or if you already have a copy of it, get it open. If you do have M&Ms, get them ready to go here. You can even open them if you want and start kind of organizing them by color. Wow, it's been a really long time since I've eaten M&Ms. Pretty excited to eat these after. Okay, so getting the lab open, possibly organizing your M&Ms if you have M&Ms. Again, if you don't, right, you can just use the data that I get here from mine. And we'll talk about other labs as well. Materials and supplies kind of talk. Okay. Okay. So hopefully you have the document open and you've made your own copy. So we're going to start with the background, right? First of all, let's have somebody tell us in the chat, a brave soul, what does a chi-squared test do? Why would we do this kind of statistical test? You can also speak if you want, by the way. I'm not telling you can't talk. If you'd rather speak instead of type, that's totally fine. Go back in your notes, right? Think about it. You did answer a question about this. What does the chi-squared test do? Why would we perform it? Identifies the null hypothesis, kind of. Destiny says, we do it to find the statistical significance between two sets of data. That's an excellent definition, right? Basically what we're going to do is, in terms of the M&Ms, right? We'll use that as the example here. M&Ms are supposed to be standardized, right? So essentially the M&M company actually says, this is how many brown M&Ms, orange M&Ms, yellow M&Ms, whatever you should have in each package, right? Because when you buy M&Ms and let's say you got all green, you would be like, what is going on, right? You expect to have a variety of M&Ms in your package. So I also have a lot of blue, Destiny. Interesting. We're going to find out if that's different from what's expected, right? So regardless, we expect a certain number of each color of M&Ms. They publish that data for us. They say, this is the percentage of blue you should have, this is the percentage of red you should have, etc. What we're going to do is we're going to take our bag of M&Ms and we're going to determine, is our sample statistically different than what the M&M company says you should have? So in other words, if they say you should have 25% blue, if mine's 80% blue, that's a little weird, right? Now in this context, it doesn't really matter, because is anybody going to get super upset because they have a different amount of M&Ms? Probably not, right? But in the first semester, we talked about this in terms of cancer, right? Cell division. Your cells are expected to divide a certain amount. For example, your skin cells should be dividing pretty frequently, right? Constantly replenishing your skin. Well, if your skin cells are dividing too much, more than the normal, right, we want to know so that we could start possibly looking for cancer and treating it. So in that case, right, we would look at what's expected. How much should skin cells be dividing? What we observe, maybe skin cells are dividing even more than they should be. Then we actually use math to determine if that's significant.
How?
Right? So,
12.
Sorry, I got to mute somebody there. So we're really looking at, is what we're seeing different than what we expect? Okay. Another way we're going to apply this to science is we're going to talk about populations and genetics. When we breed things, right, like dogs, which I hate to use dog breeding as an example because I'm pretty against it, but still, people breed dogs, right? It's not illegal, they're allowed to. When we breed dogs, we expect to see a certain percentage of dogs having a trait, right? We can use a chi-squared analysis to determine if evolution is occurring in a population, which is something that we'll talk about later. Now, the whole point of this is math, like I've said before, really makes this matter, right? If you say, well, yeah, I have a lot of blue M&Ms, that's an observation you're making, but if you can say mathematically that your M&M percentage is different than what it should be, right, that's much more valuable. So it's really basically giving you a weight behind your opinion in this case. Okay. I also forgot to mention, but it looks like most people are already doing it. We should all have our cameras on during this virtual session, which it looks like we all do, which is amazing. You don't have to have your face right in the center of the camera, right? You can tilt your computer a little bit, or, you know, have your shoulder mostly showing or whatever, right? But I want to see that you're actually there and that you're not just logging in and then piecing out and not listening to me rant about science. Okay, so what we're doing here is comparing what we see to what it should be. Now we're going to talk about the null hypothesis and relate that in here. So what is a null hypothesis? Let's have somebody tell us or speak in the chat. What is a null hypothesis? Destiny's on fire today. I guess 10 a.m. is your prime thinking time, Destiny. So it is, yeah. So there's no statistical significance between the two samples. So we assume there's no difference, right? Why do we assume that? Because we have no reason to think there will be a difference. We're going in like we have no idea if there's a difference, right? To me, my M&M bag should be a perfect representation of what M&M bags should be. So what we're going to assume that there is no difference between the percentage of colors of M&Ms that I have versus the percentage of colors of M&Ms that there should be. If you use yeah, that's fine, Jordan. We'll assume that's a full bag. That's totally fine. So what we're going to do in this lab, which I guess we'll read the background that I spent time writing, So we're going to start with a null hypothesis. A null hypothesis is a prediction that something is not present, that a treatment will have no effect, or that there is no difference between a treatment and a control. That's the fancy science language. Essentially, there shouldn't be a relationship between these two variables, right? In this case, our M&Ms should not be different from what is expected. The null hypothesis for a chi-squared analysis is always the same. How convenient. Any difference between the observed and expected data is due to chance. So the goal of the chi-squared analysis is to confirm or refute this null hypothesis. So basically, we're going to say, if there's a difference, it's due to chance, right? Another way we could say that is we don't expect there to be any difference except possibly due to chance. Once we've calculated our value, right, then we can compare it and actually do the math part here, which we will do together, where we can either accept our null hypothesis or we reject it, right? Because maybe our data is super, super different. So for example, if we find out that my M&Ms are way statistically different from what they should be, we're going to say that's not due to chance, right? It seems a little bit weird that by chance, my M&Ms would be way different. So something else must be going on, right? What's going on? Maybe there was a malfunction in the factory and more blues got added than usual, right? Then we would start looking for reasons. If they're slightly different, right, because of course not every bag is going to be identical. If they're slightly different, then we say that's due to chance, right? Of course, there's probably going to be a couple more browns in someone's bag than somebody else's bag, right? So we're basically looking at, is the difference due to chance or is it due to something else? Oh, you only have 2 yellow? Okay, so sue them. Yeah, well, so Riley, that's an interesting point, right? They kind of are setting themselves up for issues if they want to say what you should be getting, right? And then they're not actually providing you with that. Now, M&Ms, are people going to sue over M&Ms? I would not recommend, right? You're going to invest a lot of money in that. If this was something else, though, that was really, really important and mattered to you, right? Like something involving medicine or something like that, then yeah, you might want to sue, right? Or you would actually have some kind of scientific reason why it's not okay what they're doing. Okay, so what we're going to do is first we're going to write a null hypothesis. Then we're going to actually do the calculations here, talk about degrees of freedom, talk about how to find the chi-squared value. Then we're going to analyze what it means. And then you guys are going to do the conclusion questions on your own. Okay, so we're going to do some of the math together. Depending on how much time we have, we'll do all of the math together. But regardless, let's get started here. So, procedure. We'll read first, then we will do our null hypothesis. M&M packages supposedly have the same amount of each type of color that is listed on the company's website. We will take a package of M&Ms and we will test to see if it fits into these standards or is it statistically different. So pay close attention to how many categories we have, right? The categories are going to be important for chi-squared. So they actually have the different types of M&Ms, right? So in case you went fancy and bought almond M&Ms, you might have different percentages here. I just have a typical standard regular milk chocolate M&M package here. So here is the percentages that I would expect to see. I should see 13% brown, 25% blue, 20% orange, 16% green, 13% red, and 14% yellow. Mostly an even distribution, right? Although for some reason, supposedly there are more blue and orange. Just taking a quick glance at my M&Ms. Let's see if I can get them in the image there. Oh yeah, there we go. I do have quite a bit of blue. Orange looks pretty equal to the green and yellow. I have barely any red, right? And I have a pretty good amount of brown. So of course, that's just me looking at what I have already, kind of estimating those percentages. Of course, we're going to actually do the percentages. So, null hypothesis. what could we write for our null hypothesis here? There's a few ways you could say this, right? You could say there is no difference or no statistical between my M&Ms and the standard, right? Because that's actually technically what you are. Yeah, I'm doing a virtual session, but you guys can sit in here if you want to. Yeah. So you're saying basically there's no statistical difference between my M&M package and what M&M claims on their website I should have. You could also say, involving chance here, a more elevated and more fancy null hypothesis, right? Any differences I see in my M&Ms are due to chance. Now, that actually doesn't sound fancy, but it is, because really then if there is a huge difference, you're going to say, actually, no, it's not due to chance. It's something else. There's a problem, right? So those are two ways you could write this, right? You could play around with the wording a little bit and write it slightly different. But essentially, you want to say basically that either it's just chance that's causing them to be different, or there is no difference between them, right? Assuming that chance would be the reason there's differences. Again, it's kind of a language thing. Either way that you say it is fine, right? Yeah, worker's too lazy, so that might be a reason, right? Possibly somebody was like, hey, I'm going to put tons of blue in there, right? And just wanted to mess with people's minds. Who knows? Okay, so I'm going to erase those null hypotheses, though, because, you know, people who don't attend the virtual session or watch the video don't get any assistance. Okay, so now we're going to move on to actually doing the math part here. So first thing is we're going to have to calculate the percentage. I wrote here how to calculate percentage, right? Some of us probably already know that, but the main thing is first we need to figure out how many M&Ms we have. So count how many M&Ms you have in your bag. Okay, good. I hope you guys have finished counting. I was trying really hard not to speak because I know how hard it is when someone's talking and you're counting. Right, I have 55 M&Ms in my package. Elizabeth has 56. Right, you're probably gonna have somewhere around there. Already, we're noticing we don't all have the same amount of M&Ms. Yeah, and you can recount, right? To find our percentages, all we're gonna do is by color, we're going to count how many we have of that color, divide by the total amount we have, and then multiply by 100. So for example, for me, I'm actually going to tell you guys the colors, how many of each color I have, so that if you don't have M&Ms, you can be calculating the percentages at home. Okay? So for mine, there's 55 total. There are 2 red, 1, 2, 3, 4, 5, 6, 7, 8 green, 20 blue, 9 yellow, 6 brown, and 11 orange. Let's make sure that actually adds up to 55. Say 28, 30, 41, 47, and I believe, yes, that is correct. Okay, so if you have a calculator on your phone, right, you want to use the calculator on Google, that's fine. Right now we're going to calculate the percentages for all of our M&Ms. If you have your own M&Ms, obviously do it for your own. If you don't have your own M&Ms, then do it for mine, and we will compare our data. Oh, whoops, I messed up. I have 56 there. Okay, so mine should only have 19 blue, not 20. Okay, so calculating the percentage in the table, E stands for expected, yes. So you can actually start putting these into the table, right? We are first writing our observed percentages. So what you see in your bag or what you see in my bag. So for example, I got 11% for brown. Does anybody need me to show how I'm doing the percentages? Or is that something that we feel confident about? Type a 1 in the chat if you want me to kind of type out my work for the percentages. Okay. Okay, for blue, we had 19. Okay. Orange. I guess I should change this one back to 10.9 if I'm going to round. Oops. Okay, so you should make sure that your percentages add up to 100. If you want to round, that's fine. And get it as close to 100 as you can. If it's not exact, right, then that's okay. But keep in mind for all these percentages, I did the same thing here. I did the number of colors that I see divided by the total number of M&Ms, which is 55. Then I times that by 100 to get the percentage. Okay. So the next part, actually, let me make sure you guys are ready to move on. Give me a 1 in the chat if you have calculated your percentages for your M&Ms, or you got the ones from me / calculated them, hopefully. Okay. That was probably the most annoying part, honestly. The rest will go pretty fast. So now we need our expected, which guess where we get that from? What they told us. So for brown, we expect 13. Sorry, I'm getting a phone call right now. Okay, for brown, we expect 13%. Oops, I'm in the chat, not in the box. For blue, we expect 24, orange 20, green 16, 13% for red, and 14% for yellow, again adding up to 100%. Okay, so all we've done so far is calculate the percentage of colors we have, wrote down the expected percentages based on what M&M told us, right? And then now we're actually going to do the chi-squared calculation. So this is something that we've done in first semester, right? So if you already know how to do it, start doing it right now. Otherwise, I'm going to go really slowly through the brown column all the way through these two boxes to show how to do this calculation. So the first thing that we need to do is our observed minus our expected, and then we need to square that number. So I wish I had my document camera so I could show you guys my calculator, but we'll have to speak about it. So our observed was 10.9 minus our expected is 13. So we get negative 2.1. When we square a negative number, what happens? Anyone? When we square a negative number, what happens? It becomes positive, right? So we had negative 2.1. We square that, right? Remember, squaring means to times it by itself. So 2.1 times 2.1, we get 4.41. That's our first step. So you guys try for blue, either with your own data or with mine. If you're new to this, I would maybe try with my data to make sure you're doing it correctly. You observed minus expected squared. Anyone want to suggest what they got? I gave you the first two digits of it. If we do observed minus expected for blue, what do we get? And square it. I can tell you guys are like doing math because you're all really quiet. But I need someone to talk to me here, otherwise I have no idea if you guys are understanding what I'm saying. So we should have done 34.5 minus 24, right, which gives you 10.5, and then squaring that, 10.5 times 10.5 equals 110.25. Okay, yep, thank you, Kaylee. Orange, we should do 20 minus 20. We get 0. What is 0 squared? 0. That is actually really creepy that I got the exact amount of orange. Okay, for green, we should do 14.5 minus 16. We get negative 1.5. Negative 1.5 times negative 1.5, or negative 1.5 squared, is 2.25. You guys calculate red and orange and tell me what they are for my data. Thank you, Destiny. Red is 88.36. That's exactly what I got. Right, we did 3.6 minus 13, and then squared that number. Yellow is 5.29. Good. 16.3 minus 14 squared gives us 5.29. Okay, so already we should be noticing that our biggest differences, which was kind of obvious just from writing the percentages, are blue and red, right? Blue is way higher than it should be, and red is way lower than it should be. That gives us a huge number here, right? That's a signal to us that something's going on there, possibly. The next step is we take our number from this box and we divide it by the expected value. So we already did O minus E squared, right? That's this number right here, 4.41. I made all these colors so that you can kind of follow the color. But we're going to be taking this purple value and dividing it by our expected value again. So our expected value for brown is 13%. So we're going to divide 4.41. Oops. My calculator's having a meltdown over here. We're going to divide 4.41 by 13. And we should get 0.339. For blue, we're going to take our purple value and divide it by our expected value, which is 24. So we're going to do 110.25 divided by 24 and get 4.593. Here we have a 0 divided by something, which is just going to be 0. Orange is a great one. Easy to do. Green, again, we're going to take our purple value, 2.25, and divide it by our expected value, which is 16, to get 0.140. And you guys tell me what we would get for red and yellow, taking our purple value, dividing by our expected value. If you already did your own calculations for your numbers, see if you can help us out here by telling us what our observed minus expected squared divided by expected value is for red and yellow. So again, we're going to take our purple number here and divide it by our expected. Thank you, Kaylee. 6.79 is what we get for red. 6.9, okay, if we do 3 digits, 6.796. Okay, and then what about for yellow? 0.377. Okay, so that was the hardest part of this. And I know it's a lot because I could have just given you this formula, right, and had you do it. This will help you go step by step. You just have to know what each number means and what you're doing. So you have to have your observed values, you have to have your expected values. The first step will be observed minus expected squared. Fill those in. The second step will be observed minus expected squared divided by expected. So you take your number that you already had, divide it by your expected. If you're feeling a little like, I don't know if I'm getting this, right, we're going to practice it more. Again, this is something that I want you to understand on a superficial level, right? I'm never going to say, do this chi-squared and it's worth 1,000 points in the class, and if you can't do it, you're going to fail, right? It's just so you can see how we actually can use statistics in science. So the final step is actually just to add up all these last numbers that we got. So we're going to add all of these up, and that's going to give us our chi-squared value. So we're going to have 0.339 plus 4.493 plus 0 plus 0.140 plus 6.796 plus 0.377, and we get 12.145. So 12.145 is our chi-squared value, which we abbreviate as this x squared. That stands for chi-squared. So now we have to actually interpret and analyze what that number means. So our degrees of freedom is another statistics term here, which is actually our number of categories minus 1. So how many categories do we have here? 1, 2, 3, 4, 5, 6, 6. So our degrees of freedom, which we abbreviate as DF, will equal 5. Exactly. It's just however many categories you have minus 1. So if you had 50 categories, your degrees of freedom would be 49. Right? That would be insane. Usually we don't see more than like 6 or 7 categories. So we know our degrees of freedom is 5. Now, we're going to use this table here. Thankfully, it goes up to degrees of freedom is 5, right? Otherwise, we'd have to get a bigger table. And we're going to use this box right here, the 0.05% probability. That's just the common one used for science. We're not going to go into why that's used, right? If you take a statistics class, you will go into that probably later. However, in this case, I'm just going to tell you we use that column. That's what we're using. So now what we're going to do is determine if our value that we found is higher or lower than what this value is here. Does anybody remember what it means if our chi-squared value is higher? It is higher. Bella's right. Our value is 12.145. Our value for 5 degrees of freedom in the 0.05 range, right, should be 11.07. So our value is higher. So what does that mean? Excellent guess, Destiny. Right? Well, it's either going to mean that it matters or it doesn't. In this case, Destiny's right. It means that it matters. So because our value is higher than what we should get, that actually means that my bag of M&Ms is statistically different from what it should be. In other words, there's enough of a difference here that mathematically it is considered statistically significant. So what if yours is lower? That means that it's not statistically significant and that any differences you're seeing are due to chance. So Alexandria's M&Ms, maybe if your chi-squared value is like 9.5 or something like that, that would mean that your M&Ms pretty much meet the standard, right? They're slightly different due to chance, but otherwise, whatever. Destiny has a 16.647. That's super high, right? So Destiny's bag is on another level. Somebody was definitely doing something weird with that, right? Again, could be maybe there was a problem in the factory. It could be just somehow her bag got messed up versus, other people's. Colton and Jordan both have very low critical values, chi-squared values, 6.2 and 2, right? That means that yours are not statistically significant. Any differences you see are due to chance. However, mine and Destiny's, the differences we see are due to something else. What is it due to? We won't know, right? Because are we going to go investigate an M&M factory? Definitely not. But in science, right, let's say we were doing a genetics test and I found out that my M&Ms, which were my offspring, right, were way statistically different than what they should be. that's going to cue to me as a scientist, whoa, something's going on here, right? What's happening? Why is this population changing so much? Are there, are they not having any predators? Are they adapting in some way? Do they have new traits? Right? So there could essentially be a reason that we could then follow up on, right? But in this case, all we're doing here is saying it's either statistically significant or not. So when you answer this conclusion question, right, you would say my chi-squared value was, let's say that we're Abby, my chi-squared value was 8.82, which means that there is no statistical significance between my M&Ms and the standard, and any differences that I saw were due to chance, right? If your destiny or me and your value is higher than this value in the table, right, then you would say my chi-squared value is higher, right, than what is expected, which means there is a statistical significance between my observed M&Ms and the expected ones, which means it's not due to chance. Something's going on in those M&Ms. If you want to suggest what you think is going on, you can, right? And of course, it could be funny. Obviously, we're not seriously going to figure it out, but you could make a suggestion. Why do you think your M&M bag is so different if it is? So rejecting or accepting our null hypothesis, who would accept their null hypothesis? People with a value lower or higher? Lower, right? Remember, our null hypothesis said there's no difference. So if you got a value lower than 11.07, you're going to accept your null hypothesis. There's no difference. Any difference you see is due to chance, that's it. If you got a value higher than 11.07, you are going to reject your null hypothesis. I know it sounds really like intense, like I should have a gavel, like reject, right? So I would reject my null hypothesis. Something's going on with my M&Ms. They are statistically different. Then the third question is a straight up opinion question based sort of on what you're seeing in the data and kind of what people are getting, right? I would say I was ripped off too. Like I only got 2 reds. If I'm supposed to have a pretty even distribution, right, then that's not really very even. Imagine I told you guys that you had to have 30 red M&Ms. You would have had to buy 10 bags of these to get it, right? Exactly. You only got 2 yellow. What if you like yellow, right? I also know somebody mentioned to me too that supposedly all M&Ms taste the same, right? So really it's not a ripoff, right? You could also argue that. So whatever you want to say for question 3, it's just a thinking question. It's kind of analyzing, do you think that this is a problem? If your M&Ms are that different from what they're supposed to be, does it even matter, right? You might say, no, who cares, they're M&Ms. That's a totally valid answer. I got 5 brown ones, but no one likes brown. Yeah, I got a lot of brown too. I know. Actually, I think my mom likes brown, but she's the only one. We take a field trip to an M&M factory and start yelling about chi-squared. I guarantee they'll be like, what? What does that mean? So this is basically just meant to show you how to do this process. We will do another chi-squared analysis later on in the year with actual genetics stuff, right? And again, we're going to walk through it and do it together. So if you're feeling a little bit like, I'm not sure if I understood it, right? Remember, I recorded this, so you can always go back, watch the video again, right? And go through it again and say, okay, this is what I missed, or here's how to do that, or here's Miss Jamie saying accept or reject a million times and figure it out, right? We break off in fractions and make it divergent. Anyone know where the closest M&M factory is? Oh man, you guys are just wanting to go on field trips, I see, to M&M factories. But hopefully in your heart, you're understanding and loving statistics. Okay, so all you're gonna do now on your own is you're gonna turn in this lab report, make sure that you answer your conclusion questions, right? You can answer them on the document. Make sure that you have your whole chart filled out, right? And of course, you can always leave a question in your document, right? Probably in your conclusion questions. If you're confused about something specific and you want me to answer it, or you have a question about this, then just pop it down in the questions so I can respond to it for you when I grade your lab. Okay. That was so fun, right? I love statistics. Okay. So if I wasn't able to get a bag of M&Ms, yeah, so then you should fill out the chart the same way that I did, Christian. You could also get a bag of M&Ms and try it on your own if you'd like, right? Because it is good to practice doing math. Oh, the closest one is in Las Vegas. I guess we're gonna have to take a field trip to Las Vegas. I don't know. Storm the M&M factory. Let's go. Yeah, what happens in Vegas? Well, maybe that's what happened to the M&Ms. What happens in Vegas stays in Vegas. Maybe these M&Ms came from there. Yeah, they're never going to tell us. Okay, so make sure that you're getting those conclusion questions answered. The main takeaways from this, again, are the null hypothesis. We're assuming there's no difference between what we have and what we should have, right? Any difference we see, we're saying, well, it's probably due to chance, because of course, not everything is going to be identical. If we do see a difference, a statistical difference, in other words, mathematically, there's a huge gap in something, then we say, ooh, there's another reason, something's going on. And that's actually how scientists then develop an experiment, right? They say, okay, now we're going to investigate what's wrong with the M&Ms. First, we have to prove that they actually are different. Then we can talk about why. Okay. That was it. There is a code word, which actually now I'm kind of inspired based on what we've been talking about. So our code word is in the chat, right? For those of you who are new to the class and you're like, code word, what could that be? You include the code word on your lab report, right? You could put it at the top. You could put it in the conclusion questions to show that you attended the session live and that you get full credit, right? If you don't attend the session live and you watch it, you can get up to a 90% on assignments. So if you don't know the code word, you can still get a really good grade if you do everything on your own. Otherwise, yeah, then you can get 100% if you attend. So I'm actually going to erase my numbers here because I don't want people who didn't attend the session to be able to just copy my math and not think about it. So again, if you needed those numbers or you missed them somehow, you can always rewatch the recording. Can something like this happen with Twix? That's an interesting question. What do you guys think? Could we do a chi-squared analysis on a Twix? Juliana says no, and she is correct. Why? Why couldn't we do a chi-squared analysis? They are the same. Well, they don't have categories, right? Exactly. Chi-squared, you need categories. Twix is just one thing, right? So we need to have different colors, different shapes, different something so that we can put categories. So Sour Patch Kids, that could be something we could do for chi-squared because there are different colors, right? Jolly Ranchers, right? So other candies that have different colors or different shapes, those could work, right? Skittles, we will do a lab with Skittles. There's a lot of candy labs this semester. That's what happens when I make the class. I put candy labs in. Okay, otherwise, guys, we're going to end this session. Thank you for sitting through that math. I know for some of you it might have been a little bit brutal, but everyone looked like they were taking notes, writing stuff down, asking questions. Hopefully you feel a little more confident about chi-squared at this point. We will keep going through all of the statistics stuff, right? Again, do the best you can with it. This is hard stuff that I'm asking you to do because I know that you could do it. Yeah, thank you guys for telling the code word there in the chat again. Otherwise, I will see you guys next Friday. We're going to be doing a Socratic seminar on a very hard science article that I read and explain to you. You get to hear me rant and mispronounce words a lot. So enjoy listening to that, and I will see you guys next Friday.